Good afternoon. My name is Will Benton, and I'm going to spend this session telling you how to get started implementing machine learning algorithms for primarily scale-out parallelism on Apache Spark. This talk is going to have a mixture of high-level concepts and principles and some code examples, and I have some examples in both Python and Scala. And my intention here is twofold. I want the examples to appeal to a large percentage of the audience. I imagine some people prefer Python and some people prefer Scala. And in some cases, it's necessary to use different languages to talk about different practical concerns. But I hope that you'll find the examples accessible no matter what your favorite language is. And if I've used a feature that's not universally available, I'll try and explain it. Let's first, though, talk about a few reasons why you might want to build a parallel machine learning algorithm for Spark. I think it's really common for teams to develop new techniques in rich statistical or machine learning environments and then put these into production on the JVM. How many people have a workflow that sort of looks like that, where you have someone working in R or scikit-learn and then they sort of port techniques over to Spark for production? Okay, a few people. But a lot of times the framework you're using in production, like Spark and MLlib, isn't as flexible as that prototyping environment, and maybe it offers something that's close to what you need but doesn't exactly fit your requirements. So maybe you need a different distance metric or a different split criterion, and you need to sort of implement that yourself. Maybe you recently read a paper and are inspired to try out a new technique, but there isn't an implementation that you can use at scale. Or maybe you have a technique that you like from another library and you'd be happy to just use that off the shelf. You could easily integrate that into Spark by gluing it into your production code, but you'd really like to benefit from the generality of Spark and tighter integration with the rest of the ecosystem by running a scale-out implementation. As we saw this morning, Project Hydrogen is going to be super exciting for these use cases, but it's still nice to be able to extend Spark natively. So a couple of years ago, I wanted to see if self-organizing maps would be a good technique for finding anomalies in infrastructure logs. They actually turned out to be, but in order to find that out, I had to implement self-organizing maps for Spark so that I could evaluate them against months' worth of log data from one of our data centers at work. More recently, I decided that I wanted to make this code available to other users in a library, which meant solving some new problems. So the rest of this talk is the story of what I learned along the way, but we'll start with a quick overview of the self-organizing map technique in order to provide some context. We'll then discuss some of the challenges involved with taking a serial technique from a paper and translating it to a parallel technique, and we'll pay particular attention to the details we have to worry about when we're realizing a parallel algorithm using Spark's parallel collections. We'll look at what we need to do to extend our basic implementation to support more modern APIs, and we'll close with some practical suggestions to keep in mind as you develop your own techniques, including ways to ensure that your code can benefit from hardware parallelism. But let's start with that quick overview of self-organizing maps. Self-organizing maps are an unsupervised learning technique for producing a low-dimensional and discrete representation of a feature space. The basic idea is that you want to learn a map so that examples that are similar in the feature space are close together on the map. So this is a technique that's useful for visualization and dimensionality reduction, and it has some things in common with clustering. But if that explanation doesn't make a lot of sense, maybe a movie will be better. So let's see what happens as you train one of these maps. We're starting with a random map and training it with color data using angular similarity in the RGB color space to identify similar colors. As this training progresses, each example affects a smaller and smaller neighborhood of the map, until eventually the effect of any individual example in the map is extremely localized. And we can see this in progress over time. As we started with the random map, we went to a desaturated and washed out map, and finally we have identifiable areas of color in different parts of the map. In the classic online training algorithm for self-organizing maps, we'll start with an initial map. In this case, we've initialized it to random cells as we did in the movie, but there are other techniques we could use as well. We then repeatedly consider the examples in our training set. When we see an example, we identify the entry in the map closest to it, which we call the best matching unit. We then update the map to bring the entries around the best matching unit closer to our example. We do this so that the best matching unit is affected the most, and so that units further away are affected less and less. This technique is pretty powerful, and you can even fit an implementation of it on a single slide. By processing the training set in random order every time we pass through it, we prevent the accidental organization of our training data from biasing our map. There are a couple of interesting hyperparameters here, how we define the neighborhood size and the learning rate, both of which we define as functions of training time whose value decreases over time. The neighborhood size controls how much of the map around the best matching unit is affected by any particular example. and the learning rate controls how much closer to the example the affected area will get. We thus update the map by bringing the neighborhood of the best matching unit for each example slightly closer to the example under consideration. So I hope that code is pretty easy to understand at least a high level, but it isn't immediately clear how we could implement it in parallel. And a lot of serial implementations of machine learning algorithms rely on code patterns that are difficult to parallelize. So we'll look at some of those and see how to work around them. But first, why should we care about things that are difficult to run in parallel? I mean, computers are fast, right? But things that make programs hard to run in parallel also put a hard upper bound on how fast we can make them run altogether. Amdahl's law shows us that the upper bound on how much overall speed up we can get from parallelizing our programs is a function of the amount of time our programs spend in code that we can parallelize at all. So if we spend 90% of our execution time on strictly serial code, the theoretical best we could do, even if we had infinite parallelism and free communication, is just a 10% speed up. So as a real-world example, let's say you wanted to make 1 million small loaves of bread that you can cook quickly, like think of pitas or naan. You can cook a pita in like 4 or 5 minutes, and if you have sufficient oven or griddle space and you're extremely coordinated, you can cook many pitas in 4 or 5 minutes. But even if you have a large enough kitchen to cook an arbitrary number of pitas, the amount of time it takes to make 1 million pitas is going to be dominated by the 2 hours it takes for that dough to rise, which you can't parallelize at all. So it's absolutely worth it in our programs, as in baking, to find places where our technique is forcing serial execution. So one thing to look out for is algorithms that have to shuffle data. This is a problem for 2 reasons, one of which we'll see now and one of which we'll see in a minute. The first problem is that shuffling data is expensive, even on a single node. But it's even worse on a partitioned collection, where reordering in general means sending every element of the collection to another machine and forcing the rest of the computation to wait for that shuffle to complete. Another problem is algorithms that can only be specified in terms of updating an intermediate state with a single example. If you're a functional programmer, you know this kind of technique as a fold. The fold is very useful as a high-level pattern to structure serial code, but it can be a problem for parallel code if you only have a way to update a state and not also a way to combine intermediate states. Put a different way, if you have a reduce operation that takes 2 things and combines them to produce a third thing of the same kind, then you're in good shape. But if you only have a fold operation, one that takes 2 things of different kinds and returns a new thing of one of those kinds, then you may have an obstacle to parallel execution. So there are some ways we can work around these problems. The first and sort of most general principle to keep in mind is, can you realize your technique in terms of commutative and associative binary operations? If you can, then the order you run them in doesn't matter. And the more operations you have that commute, the more parallelism you can expose. So remember that I said we'd see another problem with having to randomize our training set, and this is it. If your technique really depends on the order you see data in to get correct results, it's a pretty clear indication that that technique isn't actually made up of independent parallelizable operations. Similarly, you may have an online approach for training data from one example at a time. If you can replace that with a batch approach, and you have some reduce operation or a way to combine the intermediate results from individual batches, you may be able to get a parallel implementation out of that. Finally, you may be able to use an off-the-shelf solver or optimizer, especially one that has a parallel implementation in Spark already, to realize your technique. So often the serial implementation is relatively easy, and it takes some outside-the-box thinking to use these techniques to get closer to a parallel implementation. But the good news is that for a lot of problems, someone in the community has already thought about how to apply these kinds of techniques and written it up, whether in a paper or in open source code that you can examine. So when I started implementing self-organizing maps on RDDs, I was able to start with a batch implementation that I'd seen described in the documentation for another library. I didn't even need to look at the code. The basic idea behind this batch implementation is that you go through the entire training set on each iteration, record how each example would have affected the map, and then average these effects together for the whole batch. You then come up with a new candidate map at the end of each iteration. And the key here for a parallel execution is that each batch produces a model that can be sensibly combined with other models, in this case by averaging them together. If we use a single batch per partition, then we have a natural implementation on RDDs. Now, it's important to remember that not every batch technique is amenable to combining intermediate results with a commutative and associative binary operation. And even in this case, it's possible to imagine pathological scenarios where averaging per partition maps could go really wrong, especially if you have very small partitions in your training set. But there are practical techniques to work around that problem, and I'm an engineer and not a mathematician, so I saw that it worked, and I just didn't lose a lot of sleep over it. So here's how you could take a batch learning technique and turn it into a parallel learning algorithm on Spark. This is sort of a basic template here. We're simply looping over an iteration count, and we've delegated most of the heavy lifting of model updating to our model state class. The method we're leaning on in the RDD API is aggregate, which does two things for us. First, it lets us apply a fold operation for the serial part of our algorithm. That is, the things that we're doing within an individual partition. Aggregate also lets us apply a reduce operation that combines the intermediate states from two separate partitions together. This is a very convenient API pattern and prevents you from getting your hands dirty with low-level methods where you're operating on partitions explicitly. So models can be large, and it's important to think about communication overhead. So since we don't want our model to be serialized in a closure, we're shipping it out to workers in a broadcast variable. And thinking about how you communicate large data across the cluster is important to keep in mind. But aggregate actually turns out to be the wrong implementation of the right interface. And to see why, let's look at how it's actually implemented. In a conventional aggregate, the workers perform the fold step on the values in each partition in parallel. But then they send all the intermediate results to the driver, which combines them serially. This increases memory pressure at the driver, and it also makes gnamd all sad because it unnecessarily increases the amount of execution time we can't speed up by adding workers. A better approach is to use the tree aggregate method, which has the same interface, but which performs aggregation at the workers in parallel, combining those intermediate results repeatedly, again and again, until ultimately we just have a few left that we can send to the driver to be combined serially. So you may not run into this particular problem with your technique, but the broader point is that something to keep in mind is one nice thing about declarative and functional programming is you can learn a lot from interfaces. In a lot of cases, when you're doing functional programming, like Spark with the Scala API, you can actually learn the function you need just by looking at type signatures. But once we start implementing our own parallel algorithms and caring about whether or not they're actually parallel, we need to actually look at how those interfaces are implemented, especially in cases where we have more than one implementation of the same interface. So we've just introduced a general pattern for implementing batch machine learning algorithms in parallel on serialized collections, and we've seen a couple of specific techniques for realizing those with RDDs. But you may be raising your eyebrows since it's 2018, and the RDD is a relatively low-level interface that not a lot of people like. Do we have a lot of RDD fans today? Anyone love the RDD? It's 4 or 5, 6 people. Yeah, I still love the RDD, but it isn't 2013 anymore, so we should be looking forward, and that means using more modern APIs that more people would raise their hands for if I mentioned them. Before we look forward, though, I want to talk about some of the things that are nice about RDDs, since these aspects can present additional challenges as we move to expose our algorithms with more modern APIs. And this code example illustrates what I think is the absolute best feature of RDDs. Can anyone tell me what it is? So the absolute best feature of RDDs is that this code doesn't compile, right? And by contrast, if we have an equivalent data frame program, it will compile, but it will crash at runtime. So type safety is really my favorite feature here, and I love it because it keeps me from making stupid mistakes. I especially love type safety keeping me from making stupid mistakes in machine learning programs because these can run for hours before they crash with a type error that I could have found out about at compile time. Another good part about RDDs is that you can execute arbitrary Scala, Java, or Python code in that closure argument. By contrast, you have to do some extra work if you want to expose a user-defined function for data frames, like in this case where we're scoring a model on every element of an RDD or every row in a data frame. So one advantage of RDDs is that they can actually execute any code that you give them. But this also turns out to be a disadvantage of RDDs because we can give an RDD a pathologically bad program, like this program that generates two large collections of numbers, takes the Cartesian product of these two collections, and maps each pair to the result of an expensive function and filters out some results. So if you don't have a prime density table handy, you probably don't know that this is only keeping 0.3% of its results and we're generating a lot of things and doing a lot of computations that we're going to have to throw away. By contrast, if you filter before you join, that Cartesian product is only going to generate the pairs that you're going to need to care about ultimately. Now, Spark's Query Planner will perform this kind of optimization for you if you use data frames, but not if you use RDDs. So another advantage of RDDs is that they'll operate on arbitrary JVM objects, like this naive encoding of a 2x2 matrix. But this also turns out to be a disadvantage of RDDs because of how this collection actually gets stored in the Java heap. So let's look at that now. We have an array containing pointers to two other arrays. So we have three objects, each of which has an object header consisting of a class pointer, various flags, a size field, and space for locks. And that outer array just contains pointers to the two inner arrays. So we have 32 bytes of actual data in our four doubles. But the actual amount of space that this nested collection will take up in memory, it'll depend on how your JVM organizes memory, but in many implementations, we're looking at 8 bytes per pointer and 16 bytes per object header, meaning that for this simple matrix, we actually have 64 bytes of overhead. By contrast, data frames use off-heap memory and optimized cache-aware representations to save space and improve performance. So there are a lot of good reasons to go to data frames, even in spite of the trade-offs. You have a simpler interface for your users, you have improved query execution plans, and you have better memory performance. But I think one of the coolest advantages of data frames is interoperability with machine learning pipelines. The Machine Learning Pipelines API was inspired by scikit-learn and allows you to specify entire learning pipelines as sequences of parameterized components that summarize and transform data. You can then execute these on data frames and save them to disk to use later. In this case, we're looking at k-means clustering data in a data frame. We set up our hyperparameters and a data source, and then we create a new data frame annotated with the closest cluster center for each example. So there are three key interfaces in the Machine Learning Pipelines library. An estimator takes a data frame as input and produces a transformer as output. That transformer, including a model, takes a data frame as input and produces a data frame as output. So this can be annotating a data frame with predictions from a model or transforming values by scaling, encoding, or hashing them in some way. Finally, parameters control the execution of estimators and transformers. So they can be things like model hyperparameters or simply the names of columns to take values from and write values to. These three interfaces fit together in intuitive ways and are pretty simple to use. But let's look at how to actually put them together on an implementation side. So we'll start by putting together some parameter definitions. By putting common parameter definitions and schema transformers in a Scala trait, which is like a mix-in in other languages, you'll be able to reuse the code in estimators and in the models that they produce. And this is also a common pattern in Spark's machine learning library. Here we're declaring the type of our parameter by making an instance of the int_param class, providing some user-facing documentation, and providing a validation function to ensure that a parameter takes a certain range of values. In this case, we're looking at the width of a self-organizing map, so we want to make sure it's at least 1. We'll also provide getters and setters for that parameter. Another nice thing you can do, seen here in an example from Spark's machine learning library, is actually provide individual traits for parameters that you find yourself using across multiple algorithms. So you only need to define iterations, tolerance, or seed parameters once. Unfortunately, the actual traits used in this example aren't public interfaces, but it's easy enough to make your own. So the APIs for machine learning pipelines are easy to use and form a pretty good place to get started when you're thinking about your implementation. But at the most basic level, with an estimator, you need a method to train a model from a data frame. And with a transformer, you need a method to construct a schema for the data you'll be transforming, and a method to actually affect the transformation. When you're implementing a transformer, the first place to start is with that code that transforms the schema. For many models, our estimator and our transformer will be operating on the same schema because we want to operate on examples that look like our training data. So we can both validate our schema and transform it in a single method that we can share between estimators and transformers, again, by putting it in a Scala trait. As with reusing common parameter definitions, we can not repeat ourselves and eliminate a potential source of errors and headaches. We'll see what that method that transforms and validates looks like now. The first thing we're going to do is to check that the input columns actually exist and are of the proper types. We'll then make sure that the output columns don't exist. This is optional, but we don't want to surprise the user by overwriting columns that exist. And then make a new schema. We won't actually use that newly constructed schema if we're just validating. But if this method succeeds, we know that the schema is valid. The training part, which goes in the estimator, can actually be really simple if you already have a method to train on an RDD. You can just project out the column you care about, convert that to an RDD of vectors or whatever your method expects, and train it, generating a transformer with the model you trained. So I've elided some details from my actual implementation to keep this example clear, but the point is that the actual training component of your pipeline as a first pass can at least be a straightforward wrapper on an RDD-based implementation. So we've looked at ways to improve your parallelism and some concrete suggestions for using scale-out parallelism in Spark, but that doesn't mean that you don't have to worry about your serial performance as well. Remember that Amdahl's law implies that the amount of time you spend in serial code really puts a lower bound on how long your program will take to run, no matter how much parallelism you have. So the last few suggestions I have are related to improving the single node performance of your techniques. We'll look at ways to optimize repeated similarity calculations. We'll look at how to ensure that your linear algebra code executes in a native library. And finally, we'll look at some things to consider if you want to take advantage of hardware acceleration for linear algebra. So many machine learning algorithms involve repeated distance or similarity calculations against a set of vectors that changes infrequently. In the self-organizing map example, we had to repeatedly find the best match in our model by finding its angular similarity with each entry in the map. When you're repeatedly doing a calculation like that, it makes sense to cache the magnitudes of each vector, since you'll only be using these once for every training example, but they'll only be changing once every epoch. So make sure to profile your code with and without caching these magnitudes, but it can often be a quick win. Another thing to consider is how often you touch external libraries, like your favorite linear algebra library. Each invocation is going to involve converting and copying data so that it can be operated on by optimized native code, so each invocation may have a really high fixed cost. You always want to double check how your code performs with small changes, but in general, doing as much work as possible per library invocation is going to pay off. In fact, many linear algebra libraries on the JVM won't even bother delegating to native code for operations that involve two vectors or a vector and a scalar. They'll only use the native code for matrix-matrix multiplications because the cost of marshalling the data is outweighed by the potential benefit. The implication here is that if you find yourself doing something like a bunch of dot products in a loop, you're always going to be running relatively unoptimized code in the JVM for each operation. In that case where you're doing a bunch of dot products or similar vector-vector operations in a loop, see if you can replace that loop with a matrix-matrix multiplication, which is more likely to be executed by native code. Of course, there are trade-offs to running in native code too, especially if you aren't moving a lot of data. So you'll always want to double check, again, how your code performs with these small changes. But in general, shoot for doing as much work as possible per library invocation. It can be a huge headache to get JVM algebra libraries to use native code, since you typically have to configure the code both to find the native library and a JNI wrapper. But in some cases, it can be easy. If you're using Breeze, you can simply add a dependency on the Breeze natives library, which bundles precompiled native libraries for several operating systems and architectures. Another thing to consider is the kind of values you're actually operating on. Like a lot of other frameworks on the JVM, Spark encodes everything as doubles, so you can have one implementation with a lot of flexibility. But you wind up using one 64-bit number for anything, whether it's actually a floating point number that benefits from that kind of precision, whether it's a floating point number that doesn't benefit from that kind of precision, whether it's a small integer, or even if it's a Boolean. So it's not really necessary to use this kind of memory for that. On the JVM, or in high-level languages in general, you essentially pay by the operation. If you're performing operations on a bunch of doubles, that's going to impact your performance by hurting your memory bandwidth or by using more microarchitectural resources. But multiplying two doubles isn't going to be obviously more expensive in the context of your program than multiplying two floats. And really, in the context of high-level language functions with standard control flow, you might not see a significant difference between operating on two values of different numeric types. By contrast, when you're relying on hardware acceleration, whether you're talking about SIMD instructions like those in the SSE or AVX instruction sets, or whether you're talking about GPU acceleration, you're essentially paying by the bit. A hardware instruction that accelerates a dot product across all the values that you can pack into a given number of bits is going to be faster than a high-level language implementation for doubles, but it will be twice as fast for singles, because you can pack more values into that same number of bits. So let's conclude by quickly reviewing what we've talked about today. First, we discussed why you might want to scale out a machine learning technique. We've seen how Amdahl's law puts an upper bound on the kind of speed-ups we can get from parallelizing our programs, and we've considered some of the code features that make machine learning algorithms in particular difficult to parallelize. We also discussed some strategies for parallelizing machine learning algorithms, using batch algorithms instead of online algorithms, reformulating our algorithms in terms of commutative and associative operations to enable more parallelism, and reformulating our optimization problems in terms of solvers that have parallel implementations. We saw how developing libraries for Spark can require you to be comfortable with both relatively low-level interfaces like the RDD and with extending higher-level APIs like data frames and machine learning pipelines. Finally, we considered some techniques for ensuring that our programs run efficiently when they have access to native and hardware-accelerated algebra libraries. And if you take a step back, that really brings us back around to Amdahl's law, albeit within a processor instead of across machines. Since copying data to and from the JVM is a bottleneck, we need to make sure that the amount of time we spend copying data is minimal relative to the speedups we can get from exploiting parallel vector math in our CPUs and GPUs. As we saw, we want to ensure that we interact with the surface of the library as infrequently as possible, using matrix-matrix operations whenever possible, and using the narrowest data types that we can get away with. I hope you'll leave this talk inspired to scale a favorite or new technique out, but I'd love to hear from you in any case. Here's how to keep in touch. I'm willbe@redhat.com, and I'm also willbe on Twitter and GitHub. I have a personal website there on which I regularly post blog articles related to my work, which is almost exclusively machine learning and distributed systems. And that self-organizing map I mentioned is part of the Silex project, which is a library of helpers for Spark that we've extracted from applications we've built at Red Hat. Silex and several other applications are available from the radanalytics.io community. Please check it out and let us know what you think. And if you're interested in publishing your own code as libraries, let me encourage you to also attend Spark for Library Developers later this evening in room 2014. Thanks for your time and attention. I think we have a little bit of time for questions.
Excuse me.
So let me restate the question, and hopefully I heard correctly. The question is, are there some algorithms for which using RDDs is actually better than using data frames? I think there probably are, right? And I think the question is like, is it something that's simple enough that you won't benefit from query planning, and is it something that's again, you know, where sort of encoding and decoding that you'd have to do with a data frame program would slow you down a lot. I think certainly for something like k-means, a lot of things that you can solve with the high-level optimization primitives, RDDs may be a great option for your implementation. Certainly in ML lib, a lot of things, or in ML pipelines, a lot of things are implemented in terms of RDDs still. Yes? I don't know. Why SGD is not available in data frames, I don't know. Sorry. Yes? So the question is, how would you bypass the double requirement to use a smaller type? And I think the answer is you're sort of getting into sort of specialized code at that point. And you give up really the opportunity to interoperate with ML lib, which is typically focused on vectors of doubles. For a lot of the things I've developed, you sort of delegate to another library anyway for the implementation. In this case, you would be operating on basically marshalling to singles or some lower precision numeric type once when you start training and then going back. All right, well, thanks so much, everyone. Have a great conference.